Hey everybody, this is Scott Meek. I'm a trainer here at Diesel Laptops, and I'd like to welcome you to the After Treatment Temperature Diagnostics webinar. Before we get started, I want to let everybody know that you are on mute, and we do that for background noise, but you can still talk with me. All you have to do is send me a chat. There's a little function that you have. If you go to the top right of your screen where your little GoToWebinar toolbar is, you can actually chat questions in. But before we get started too far, can anybody send me a chat and just let me know if you can hear me? Because I'm sure that you all can, but it's saying that my audio is not connected. So if I can just get one or two people to verify that you can in fact hear my voice, I would appreciate that. And again, if you just use that chat function, and if you just want to, shoot something over that just says, "Yep, got you," awesome. Thank you, Christina. Thank you all so much. So today, we're going to be going over after treatment temperature diagnostics. And again, as we go through this software or this presentation, feel free, if you have a question, feel free to just chat it over. Again, you're on mute for background noise, but we can still communicate that way. So any questions you have, feel free to shoot them over. Now, during the course of this presentation, you're going to see me do some PowerPoint slides, and then you're going to see me go to a tablet and do some drawings. And I'm going to go ahead and warn you that my drawings are terrible. But hopefully it'll kind of help you get the idea of what I'm trying to explain here. So to get started, one of the things I want to say as a technician of going on 17 years now, when you're doing diagnostics on after treatment systems, here's the thing. We've separated these webinars into two different webinars. We have the after treatment temperature diagnostics webinar, and then we have the SCR diagnostics webinar. And we do that because, for one, I need about an hour and a half on each one of these. I really need more, but two, when you're looking at after treatment systems, when you have an emission-related issue, you need to look at the entire emissions package as a whole, right? If we're dealing with 2010 and newer, then it's pretty good chance we have a DOC, a DPF, and an SCR catalyst. And the thing is, when we're troubleshooting these systems, I like to break these systems up into two different sections. So even though the DOC, the DPF, and the SCR catalyst are all part of the emissions, we need to look at the DOC and the DPF as one piece and the SCR as another, because the DOC and the DPF have a very particular function. And that real particular function is to capture ash, to capture soot, and then under high temperature, oxidize that soot, and which will convert it from a soot, a solid particle, into a gas so it can escape the filter. That will leave us with only ash in that filter. So this section of the webinar, the temperature diagnostics, we're focusing on the regeneration side of the system. So 2007 to 2009, this is all the vehicles have. And then 2010 plus, they continue to use this system, but they add SCR. So my goal is to make sure you understand how the regeneration side of the system works. When we run regenerations, what are the temperatures telling us, so we can troubleshoot these vehicles much quicker and easier, because one of the things that I tell technicians all the time is, when I force a regeneration with my service tool, if I hook my computer up and I force a regeneration, a stationary regeneration, I'm doing that for one reason. I'm doing that for diagnostics. I'm not doing that to just regenerate the truck. Now, after the regeneration is complete, if that's all it needed, perfect. But generally, again, generally, if a truck comes to you for regenning consistently or regenning too often, running a forced regeneration on it is not going to fix it. There's something else going on we need to address. So when I run a forced regeneration, I'm doing that with the assumption that I'm going to diagnose it. And the thing is, if you watch a regeneration take place live and you watch the temperatures and you pay attention to the temperatures, you can almost diagnose what's wrong with that after treatment system just by doing that, right, without lifting a single wrench. So I'm going to explain some of that to y'all today, hoping that you can retain some of that and put it to work, be a little more efficient, make a little more money, happy customers, happy boss, happy life. So here we go. What is after treatment, right? After treatment systems are a set of components that are designed to lower emissions by preventing harmful combustion exhaust molecules from entering the atmosphere. It's pretty simple. Our after treatment system, in a nutshell, we're going to capture or change the structure of these harmful molecules. So we're either going to completely trap them, or we're going to try to change that molecule from something hazardous to something far less hazardous, right? And that's what we're trying to accomplish with an after treatment system. So what does the engine have to do with it, right? Because today we're talking about after-treatment systems. What does the engine have to do with it? The engine has everything to do with it. One of the things that I really want to stress is when we have trucks come in with regeneration issues, what happens with a lot of technicians, and not all, but a lot of them, they almost get tunnel vision. What happens is, and I'm guilty of this earlier in my career as well, you see a regeneration fault, and you automatically assume that something's wrong with the regeneration system. And when you think of the regeneration system, you're thinking of the DOC, the DPF, if it's 2010 plus, the SCR catalyst, and then all the sensors that coincide with that. But you need to get out of that tunnel vision, because after treatment systems are a set of components designed to work in conjunction with an engine that's working properly. So if your engine's not working properly, if you have any type of engine-related issues that can cause smoking, skipping, low power, drivability, performance, all of these things, oil consumption, coolant consumption, poor fuel, all of these things can lead to after treatment issues. So one of the things that I like to say is, when we refer to upstream and downstream, when I say upstream, I'm talking about the engine. When I say downstream, I'm talking about the after treatment. Upstream issues turn into downstream catastrophes, right? So what may start as a very small issue up top, an EGR cooler that you're just leaking just a little bit of coolant, that starts trickling downstream and turns into a issue where your DOC is completely face plugged and it can't regenerate. It's not efficient, so your temps never get hot enough. And then your DPF's full of soot, it's full of ash that it can't regenerate. And then the next thing you know, your engine can't get exhaust out. You're derated and you're sitting on the side of the road. Okay, so that little small upstream issue turns into big problems. So let's make sure anytime you have an after treatment issue that you focus at least half of your attention on the engine itself, okay? Now, just a fun little fact for you, 80% of regeneration issues start due to a failure on the engine. Now, that doesn't mean that sensors don't fail. That doesn't mean your exhaust thermistors aren't reading bias. That doesn't mean that your diesel particulate filter differential pressure sensor isn't reading bias. That's not what that means. Obviously, sensors do fail. Obviously, components do fail. But 80% of all regeneration problems are happening because of an engine-related issue. So what we see in the field happen quite often is a truck will come in, the ash load or the soot load will be extremely high in the filter. They'll not really know what to look for, so what they do is they perform a regeneration. I understand. They send the truck out, and then it's back, right? Or maybe the truck comes and you check it and you say, hey, the ash load's too high, so I need to clean this filter. And then you pull the filter off, you have it serviced, you reassemble it, you run a regeneration, you let it go. And then 3 weeks later, the truck's back. And that's because you never address the root cause of the problems. Okay, so do filters fill up with ash on their own? Absolutely, that's what they're designed to do. But you're talking 200, 300,000 miles. If you've got a filter that needs to be serviced or a truck that needs to be regenerated daily, and you've only got 50, 100,000 miles on this truck, you've got an upstream problem that's leading to this. So we have to address that, okay? Now, another fun fact, between 40 and 50%, now hear me, if I said that 80% of regeneration issues start with a failure on the engine, what if I told you 40 to 50% of all regeneration issues that enter into your shop for diagnostics have been previously diagnosed within 2 weeks prior to your shop getting that job? What this means is almost half of all trucks that are worked on because of regeneration issue break down again because nobody took the time to check the engine, okay? So I just want to stress that. So let's kind of get into the basics of this. Let's talk about the components and what they do and how they work together. So we're talking about the regeneration system, and the regeneration system was added onto American vehicles on highway in 2007, and the regeneration side is still on the vehicles today. So what we refer to as the regeneration side of the system is the DOC and the DPF assembly, because they have a job to capture ash, to capture soot, to oxidize that soot through high temperatures, turn that soot into a gas so that chamber can breathe again. Once that chamber is slapped full of ash, we will have to service that assembly. So this was primarily introduced in 2007 here in America. Regeneration is not new. Okay, these systems were actually out in Europe since 98 and 04. So this is not a brand new technology. It's just, if you don't work at a dealership, then you may be a little bit behind, and that's okay. We're gonna help you get caught up on this. All right. So the first major component that we come to when you're dealing with a regeneration system is our DOC. And a DOC stands for diesel oxidation catalyst. Okay. Now on your medium and heavy duty vehicles, the next large component that we're going to come to in the exhaust flow will be the DPF, the diesel particulate filter. Okay. So we're filtering particulates, right? We're catching that soot, we're catching that ash. Now, depending on the manufacturer, and a lot more depends on the size of the vehicle, we may have an after-treatment fuel injector. Okay, now an after-treatment fuel injector is a fuel injector that's mounted generally after the turbocharger, before the inlet of the DOC. And it has one job. It's to spray raw diesel fuel downstream so that that fuel can react with the DOC, the diesel oxidation catalyst. And when you have that fuel hitting that DOC with the precious metal wash, you're going to get a chemical reaction, which is going to give you a lot of heat transfer. You're going to go from 500-600 degrees, and because of that fuel hitting that face of that DOC, we're going to take that 500 and 600 degrees and we're going to turn it into 1100-1200 degrees. Okay. We have temperature and pressure sensors. If we have an exhaust stream that's getting up to 1,000, 1100, 1200 degrees, we should probably monitor that for safety, right? But it's not just for safety, it's for diagnostics, it's for ECM diagnostic tests, it's for us as technicians to figure out the problem. So it's really nice to have these there. And then of course, we're going to have some sort of pressure sensor at the DPF. Now what you generally have is what you see on the screen, and that is a DPF DP, or a diesel particulate filter differential pressure. Now if you have a differential pressure sensor, you're going to have a tube before the DPF assembly, and you're going to have a tube after the DPF assembly. And what it's measuring is the difference in pressure. But what you're truly measuring is flow. Okay, so that's what helps us determine just how restricted our filter is. So we're going to use those values of that sensor during our diagnostics. We're going to look at our differential pressure sensor voltage, and we're going to figure out just how restricted we are. So let's start with that first big component. Let me break this system down into sections, because what I want to do is I want to tell you what they are and how they work and some of the failure modes, right? So let's talk about that DOC first, that diesel oxidation catalyst. The primary goal, the numero uno, the number one goal in a modern diesel of the diesel oxidation catalyst is to create heat for regeneration purposes. Okay, its secondary purpose when not in regeneration is because of the makeup of this assembly. It's also going to provide some reduction of hydrocarbons and NOx. Okay, so hydrocarbons and NOx are two of the things that this emission system's trying to break down and either modify or completely catch. So the DOC does have two functions. Again, it's going to reduce hydrocarbons and NOx slightly, but its number one goal is to create heat for regeneration purposes. Now, these DOCs, these are usually designed with a ceramic material, which have a precious metal coating, which reacts with diesel fuel to create heat. Now, I wanted you to hear that it's usually designed with a ceramic material with a precious metal coating. Now, here's why I'm telling you this. When you have a DOC that's failing, it's what they call efficiency loss. Our DOC is no longer efficient. And when our DOC is not efficient, there's a reason for that. If we've lost efficiency, there's a reason we've lost efficiency. Now, again, when you create a DOC, they get the ceramic substrate. They dip it into a aluminum oxide slurry mix. In other words, they take a liquid that has aluminum oxide, they dip that ceramic substrate down into that liquid. What that is think of that kind of like a binder or a glue or an adhesive, right? And then they're going to dip it, or what they call impregnate, this assembly with precious metals, okay? And what that means is they're going to inject or either dip, depending on the manufacturer, they're going to put precious metals inside of those cellular walls, okay? And they do that so we have something to react with. Those precious metals, the platinums, the palladiums, the rhodiums, these are the materials that are in this DOC, and without those precious metals, you won't have the chemical reaction with the diesel fuel. So our DOC has to have these precious metals, or when we spray diesel fuel downstream, if the diesel fuel reacts with the ceramic, nothing's going to happen much. We need the fuel to react with the precious metals in order for that reaction to take place. Those precious metals are also going to help reduce hydrocarbon and NOx through a chemical change, right, through a molecular change. So there's multiple shapes, there's different sizes depending on manufacturer, but they all have the same basic principles. Now, if you bear with me, what I'm going to do is I'm going to jump over to some of my kindergarten sketches here to give you an idea of what's happening. Okay, so what I'm going to do right now is I'm going to sketch you out a DOC, because we know that it's a precious metal wash. We know that the precious metals are adhered to the ceramic. Now, why is that important that I'm talking about that? When you're dealing with something that's adhered to something else, what you have is something that can eventually unadhere, right? Think about the headliner in your car that can start sagging. Thinking about the paint on your car that can start peeling. Think about anything that's adhered to something else. Eventually, through outside sources, it can unadhere. Well, that's a problem, okay? So let me draw you here an example of what we're looking at. On the DOC, if I drew the inlet and I drew the outlet, okay, what you're going to notice is if you were to look at this, and of course I've got a much larger blown up version of this, what you're going to see are a bunch of little tiny cells if you were to look at the inlet or the outlet. And all these little cells, it's kind of like a honeycomb substrate. So if this was the inlet and the outlet, what happens is if my exhaust gas goes into this chamber on the inlet, my exhaust gas will exit that same chamber on the outlet, okay? So the same chamber the exhaust goes in is the same chamber the exhaust goes out, which means our DOC is a pass-through device. So what I'm going to do is if I took my DOC and I was looking at it lengthwise, and I was to cut it in half lengthwise, kind of like you would do a sub roll, and you were to open up that sub roll or that bread, what you would see is a bunch of these little chambers, right? So we'll say this is the inlet of the DOC, and this is the outlet of the DOC. Inside are chambers, and in those chambers are going to be those precious metals, and those precious metals are going to be lined along the walls of that chamber. Again, there's usually more than one precious metal that's in there, so I'll use a couple different colors to just kind of give you the idea. And they'll be all interwoven with each other, okay? It's not just like there's one precious metal in one cell. They're all kind of mixed together here. So what happens is, as the exhaust gas, close that down, as the exhaust gas, give me just one second. All right, as the exhaust gas comes in, what it's basically going to do is it's going to go into a chamber. And then it's going to continue its way through that same chamber. And as it passes through this chamber, it's going to react with these precious metals that are along the walls. Now, if for some reason your DOC assembly was, poisoned, as they call it, if we got a whole bunch of carbon or coolant or, fuel, a lot of different substances upstream that came downstream, what would happen is a thick coat of carbon would end up covering up these lines of these walls, right? This carbon's just thick, and it'd start lining these walls up. And what happens is if the carbon lines up the walls, well, we can still get some exhaust gas through there, right? We can still get it through this area. Problem is there's no way for it to react because there's no way that it can touch the precious metals. So if that happens, we're going to have a loss of efficiency, okay? The next thing that could happen is these precious metals that are here could unadhere. And if they unadhere, basically they're going to start going downstream, and they're going to get caught by the DPF assembly, right? That's a problem too. So what I want you to understand about this is the DOC has a precious metal coating that can be covered up by carbon or a combustible substance that came out of the combustion chamber, or it can unadhere. But it's also a pass-through device. So the chamber that the exhaust gas enters, the exhaust gas exits. And it's important to know that because that's going to, if you know that, it's going to make sense when you're in diagnostics. If you know it's a pass-through device, when you start diagnosing it, you're going to be able to see how it reacts, right? I'm going to explain that as we get a little further. So if you bear with me, I'll jump back to the PowerPoint here. All right. The next major component that we have is going to be our DPF, our diesel particulate filter. Now the DPF has a job, and that job is to capture ash and soot, to capture the particulates coming from the engine. When you're dealing with a diesel engine, your diesel engine is going to emit particulates. It's just nature of the beast. So, 20 years ago when particulates were being emitted, you might could see some smoke coming out the tailpipe. Wasn't a thing. Nobody cared. It was a sign of a good engine, right? Well, now you don't see that. You shouldn't see that. If you see smoke coming out the tailpipe of a modern diesel engine that has a DPF and DOC, something's wrong. When you're dealing with 2007 to current, if you have smoke emitting the pipe, something's wrong. So the term is, if it's smoking, it's broken, right? Now, the problem is if your DPF assembly is working correctly, it's going to mask that, right? So you could have an engine that's smoking, and you might not be able to tell because your DPF is capturing all that. So that's the problem. You might have a smoking engine, something's wrong, and they never realize it because they never see smoke, so they just keep driving. The next thing you know, he's derated, he's sitting on the side of the road, and he can't go anywhere because his filter is completely stopped up with soot and ash, and his regeneration system can't overcome how much is going downstream, right? So just something to be aware of. So let's talk about that DPF, that diesel particulate filter. DPFs are designed to trap particulate matter, which is then to be burned off at a high temperature during regeneration. Usually designed with a cordierite or silicon carbide substrate encased in the metal housing. Multiple different sizes and shapes depending on manufacturer, same basic principle. Must be cleaned of ash at certain intervals for a long life. So we can regenerate these chambers if it's full of soot, but if it's full of ash, we can't. We can't burn ash down any further than ash is already burnt. So again, I'm going to jump over to my elementary drawings here and give you an example. So if I'm dealing with a DPF, if I were to look at the inlet and the outlet, we're going to see a lot of the same similar characteristics, right? We're going to have cell walls, right? Or chambers like we did on the DOC. The difference is this. If my exhaust gas enters this chamber on the inlet, it's going to exit this chamber and this chamber on the outlet. Here's why. If I was to look at the inlet, unlike the DOC where every cell is open, on a DPF, every other cell is open. So this cell would be blocked, and this cell would be blocked. And then this cell would be blocked, and this cell would be blocked. And this is going to be you're going to have to look close because these are tiny, tiny little cells here. But basically every other cell is going to be restricted in the front. Okay, it's going to literally be blocked off. Then on the rear, every other cell is going to be blocked off. The opposing cells, the opposite of what's happening on the front. So what happens is, if my exhaust gas enters this cell, then basically, or excuse me, if my exhaust gas can't enter the cell, I'm sorry, I apologize, got ahead of myself. If my exhaust gas enters this cell, the open cell on the front, by the time it gets to the back, it's blocked off. There's nowhere it can go. It has to go here and here. Okay, let me explain that. Let me do the same concept. Let me take the DPF lengthwise and let me cut it in half and spread it open like a sub, right? What you would see would be chambers. Now, if this was the inlet of the DPF and this was the outlet of the DPF, here's what happens. As you're driving, exhaust gas comes into your DPF assembly. Now, it can't go here, obviously, because this is blocked off, and it can't go here because this is blocked off, and the same goes for this. It can't get to these chambers. So it's going to have to go to a chamber that's open. When it goes to this open chamber, it continues down this chamber, and it basically hits a brick wall. It stops. There's nowhere for it to go, except there is. Because what happens is it stops here, but this wall right here, each one of these walls are going to be porous. This means they're a wall flow filter. It's not a direct pass-through, it's a wall flow. So once the exhaust gas hits this wall here, what it'll do is it will redirect through this media and then come out. So what it's doing is as the exhaust gas comes into this chamber, it's allowing the gas to escape. However, the ash and the soot, the solid substrates cannot. The solid substrates can't fit through that porous media. Only the gas can. So as you're driving down the highway or using the vehicle, what's going to happen is your cell walls are going to start to fill up with ash and soot. We're going to say pink is ash, red is soot. Okay, so we're starting to fill up with ash and soot. Now the problem is we have a sensor called a DPF-DP, or maybe it's just a single sensor, a single 3-wire gauge pressure sensor. Okay, it just depends on manufacturer. But DPF-DP is the most common. Now what's going to happen here is I've got a sensing tube here, and I've got a sensing tube here. And my sensor has 3 wires. Okay, we have a reference, we have a ground, and we have a signal. Our reference and our ground is going to be used to power the sensor. The signal is what goes to the ECM to let the ECM know how restricted this is, and it does that by using a voltage rating, right? So if we're talking about a standard DPF-DP, our key on engine off voltage is going to be somewhere around 6 to 8 tenths of a volt, okay? And then full, complete, stopped up DPF, couldn't be any more stopped up, you're going to be somewhere around 4.3 to 4.5 volts, right? But that's severe, severe, severe. Vehicle probably won't even run if you reach 4.3 to 4.5. So what happens is as these chambers start filling up with soot and ash, what happens is our signal voltage starts to go up. And it goes up to the point where the ECM realizes, you know what, my pressure is really high, and it's because my chambers are getting full of soot and ash. And if my chamber is full of soot and ash, guess what happens? I won't be able to breathe. Remember, engines are air pumps. We have to get air in, we have to get air out. So if the air that we're getting in, we can't get out, then the engine won't run, right? So what happens is a regeneration will take place. We'll get extreme temperatures, and then we'll take all of the soot and ash, we'll oxidize the soot, turn it into a gas, so it will escape, and then we'll be left with nothing but ash. So then we drive down the road some more, and then we start building some soot, we start building more ash, we start building some soot and some more ash. All this constantly happens. Our chambers get full again. We run a regeneration. We have to oxidize that soot. So what happens is we run a regen. We open up that chamber again. And then what happens is once we open up that chamber again, guess what we're left with now? A little more ash. And then this constantly happens till we get a little more ash and a little more ash and a little more ash. And this just keeps going until this entire chamber, or all of these chambers, would be full of ash. And when all of these chambers are full of ash, then our engine can't breathe. And if our engine can't breathe, we can't run. So once we're full of ash in the assembly, we're going to have to pull that filter down. We're going to have it serviced and cleaned and get that ash content out. So that's what happens inside of a DPF during regeneration. And that's what happens not during regeneration as well. So hopefully that helps a little bit and explains a little bit to you there. We've got a lot more to go through, but hopefully you're gaining some knowledge here.